I'm happy to welcome all of you to the problem discussion session of RBGG 2021. May I request Professor Ampa Kumar to chair the session.
Thank you. As told earlier, we will have this problem session. In every such meetings, problem sessions are very significant because I know a wonderful case where there were lectures in physics by Pauli, Albert Einstein and others, compiled by some publishers, and the program was organized by Abdus Salam, who later became director of ICTB. And it turned out that out of the 10 contributors of that booklet, I think 6 or 7 got Nobel Prize, including Abdus Salam. And all the discussion in the problem booklet was some problems that was discussed during those get-togethers. So I give a lot of significance for the problem sessions. Now I invite Arvind, who is a professor in the Institute of Mathematical Sciences, Chennai, to start his presentation. Roughly, we will now spend about 15 to 20 minutes for each of them. And in fact, Sandra Kingan from City University of New York is also presenting. So 2 confirmed. And as the discussion starts, we have more people, then we will allow them also. So Arvind, please.
Sure. Thank you. Thanks Aparna and Vijay for giving me an opportunity to present this little question here. So just by way of background, this question kind of naturally occurred to me towards the end of the 2 initial talks that Peter had given way back in March. And then I was caught up with many other things and could turn to them only seriously in the last 2-3 weeks. I then had an email discussion with Peter and got so many interesting inputs and insightful suggestions from him that it's quickly evolved into something that looks like an interesting bunch of questions. Not too many answers yet, but looks very promising and very interesting. So I'm going to present it in a certain context in which I look at these problems. It may not be very mathematical because I'm kind of a mixed bag, trained in mathematics to begin with, but more of a computer scientist as a professional. So here we go. So the question is, given a graph, you want to check whether it is the commuting graph of some group or not. So this was the question that I had asked Peter right in the beginning, and so here are some thoughts. So this is what I call the realizability problem. I looked up literature and there are several papers that are written on it, but none of them seem to be really from an algorithmic angle. So, okay. So more on that. I know most of you are trained basically as mathematicians, but getting the algorithmic perspective will be simple, intuitive, thing which I'll share with you. So is a given undirected simple graph the commuting graph of a group? We will define the commuting graph as we won't remove the center from the graph. So it's the undirected simple graph with vertex G, and we put an edge between a pair of elements of the group if they commute. So it's a diameter 2 graph, as we know, because the identity is connected to all the vertices, and there are more edges. And the center in particular is also connected to all the vertices. What are we looking for? So when we say realizability problem, there could be 2 perspectives we could take. One is find mathematical characterizations of commuting graphs for all groups. That would be ambitious. That means I would like to say, given a graph, that it's the commuting graph of a group if and only if these conditions are satisfied. That would be like a dream theorem. But if we could do it for special interesting classes of groups, like for abelian groups, we can say that the complete given graph is the commuting graph of an abelian group if and only if it's the complete graph. So like that, we want to do it for all, what happened? I don't know why I can't. Can you can't see the. Can you see the bottom line?
The bottom line is missing, sir.
Yeah.
You can adjust the zoom of your presentation so that it will be visible.
Yeah, let me do something. Okay. So first is the mathematical approach, if you will, and the second is the computer scientist approach, which is that I give me a graph. I want to design an algorithm which will take the graph X as input and tell you whether it's the commuting graph of a group or not, and as efficiently as possible. And ideally, what we would like is to also find a group whose commuting graph it is, in case the answer is yes. So this is the realizability problem. So what is the motivation and related questions? So one, I think, important motivation is a very well-known problem in the field of algorithms. It is that you're given two groups, G1 and G2, by their multiplication tables. So you're given it explicitly. You have the n group elements labeling the rows and the n elements labeling the columns, and the ijth entry is the product of I and j. So that's the multiplication table of a group. You're given the two groups by their multiplication tables, and we want to figure out if they're isomorphic groups or not. What is a good algorithm for doing it? And just by way of telling you what an algorithm could look like, there is a very simple group theoretic n to the power log n time algorithm, where time is intuitively measured in roughly what you think as basic steps, which are intuitively easy to do, like multiplying two elements of the group is a one-step operation. So the n to the log n algorithm would simply be to find a log n sized generating set for G1, and then simply if there was an isomorphism from G1 to G2, this log n size generating set would have an image of size, the same size inside G2. And we could try all n to the power log n ordered subsets of G2 as candidate images for this generating set S of G1, which is of size at most log n. And using the fact that it's a generating set and the mapping is a homomorphism, you can use the rule that pi of xy is pi x into pi y to see whether it's actually a well-defined mapping at all and whether it gives you an isomorphism from G1 to G2. And if G1 and G2 are isomorphic, surely one of these mappings will succeed. So that's a simple n to the power log n, essentially brute force algorithm, but the fact that groups have small generating sets helps us here. So a very important open question is whether we can do this in n to the power constant time, say n squared time or n cubed time. For example, if G1 and G2 are a billion groups given by the multiplication tables, then you can find a very easy algorithm that runs in order n squared time, essentially quadratic time, where n is the number of elements in the group. You could even do it in linear time with a bit of careful bookkeeping. So like that, you can, people have explored this problem for various special classes of groups, but haven't got much better than n to the log n. There are some specialized results which I won't go into. So what I believe should be an easier problem is, because it's a larger equivalence class, given two groups G1 and G2, do they at least have the same commuting graph? That's an interesting open question for which I don't know an n to the log n algorithm, because it's not an isomorphism of groups question anymore. It seems to be more of a combinatorial question. I don't know how to exploit the group structure here. It should be an easier problem because the equivalence classes are larger, but maybe it's a harder problem. Okay. So this is something while I was doing literature survey, I discovered this is also an algorithmic result.
Sorry for the interruption.
Yeah, please.
So the previous last line, you mean to say, suppose the commuting graphs are isomorphic, are the groups isomorphic?
No, I'm just asking, given two groups G1 and G2, by the multiplication tables as input.
Oh, okay, okay. So
can you
efficiently
efficiently
have a graph theoretical property?
Yeah, yeah. No, not a graph theory. An algorithmic result. Can I check how efficiently can I check if they have the same commuting graph?
Okay.
By same commuting graph, I actually mean isomorphic.
So without looking into the isomorphism between G1 and G2.
Without looking into the isomorphism between G1 and G2. Because if G1 and G2 are isomorphic, then I know they have the same commuting.
Okay, fine. Thank you.
Yeah. So here is a very simple, nice thing, which is also algorithmic. Given any n-vertex graph, it's by these people who studied realizability of graphs by both semigroups and groups. I don't remember their other results, but this one is a very general one, and it's easy to read and understand, so it caught my eye. Given any n-vertex graph with at least 2 vertices of degree n-1, you can actually show that we can always find an n-element semigroup for which it's the commuting graph. And the idea is really simple. I won't go through the details because it will take up too much time. So let's say 0 to zk minus 1, there are k elements of degree n-1. So k is at least 2. What you do is you take one of them, call it 0, and make it the multiplicative 0 of your semigroup, and make the other one, or the remaining ones of degree n-1, multiplicative annihilators. So that z into v equals v into z equals 0. And then what you do is, if vi vj is an edge in the graph, you set their product either way as 0, vi vj and vj vi both as 0. If vi vj is not an edge, then vi vj is, let's say, z1 if I is less than j, and vj vi is 0. And define vi squared to be 0 for all the i's. Then it turns out that the product of any 3 of them bracketed whichever way is always 0 because it will get annihilated. So associativity is taken care of, and the rest of it is easy to check. So an interesting question here, of course, is what about graphs of where there's at most 1 vertex of degree n-1? Can we, given any arbitrary graph, can we check efficiently whether there is an n-element semigroup which will realize it as a commuting graph? I don't know the answer. Moving on, what can we infer about the group from the commuting graph? Suppose X is the commuting graph of the group G, then we know that the center of G is all degree n-1 vertices. These are the elements that commute with everybody. The closed neighborhood of any vertex is the centralizer of that vertex. This is precisely the set of all vertices that commute with X. So we know the centralizers of every vertex. So therefore we know, for example, that the degree of, so because it's a closed neighborhood, the degree of X plus 1 divides n, and the conjugacy class of X is n divided by degree of X plus 1 by Burnside's lemma. And we also know that the maximal abelian subgroups of the group G have to be the maximal cliques of X. Here is a quick way of seeing it. Suppose you have a clique, and then look at then everything in the clique corresponds to elements that commute with each other. So look at the subgroup generated by these elements. If this is the entire subgroup, well, then the subgroup itself cannot grow. But maybe if it's a maximal subgroup, then it absolutely cannot grow. Otherwise, there's always some element of the subgroup lying outside which will be connected to everybody because it's part of the subgroup, in which case it will surely expand up to the subgroup. And if it's not the maximal abelian subgroup, there is a larger abelian subgroup. So there must be other vertices outside which are connected to everybody inside. So simply greedily grow starting from a vertex to the maximal clique that you can grow containing that vertex, and that will give you a maximal abelian subgroup containing that vertex. So you can find out all maximal abelian subgroups. These are the 3 immediate things that you can do, and it's not clear what much more you can do from the commuting graph of a group. let's see what we can squeeze out of this. So you can recognize groups of size p cube. That's one thing that you can easily do. Let me just describe that quickly. Of course, if G is a billion and of size P is a prime, of course. So if G is a billion, then its commuting graph is the complete graph. So only the non-abelian cases are interesting. Center is non-trivial, and if the center were of size P squared, then G quotient, the center will be cyclic, which will mean the entire group is a billion again. So the center must be of size P if the group is non-abelian. So what are the maximal abelian subgroups of this? Remember, from given the commuting graph, all we can really find are the cliques, the maximal cliques. The maximal abelian subgroups, it turns out, are all of size p squared in a group of size p cube. And in fact, they arrange themselves in a very nice structure. There are exactly p plus 1 many maximal abelian subgroups, all of size p squared. So that accounts for, and they all intersect at the center. So you can see that p square minus p into p plus 1 plus p is p cube. So that accounts for all the elements of the group. So the commuting graph of a non-abelian group of size p cube looks like, you can imagine, a kind of a flower with p plus 1 petals. Each petal is a clique of size p squared, and all of them intersect at the core, like the combinatorial sunflower lemma. So the core is the center, has p elements in it. So it's easy to detect, and the moment we see such a graph, we can recognize it. Okay, moving on, the immediate generalization is to ask for the commuting, whether we can recognize commuting graphs of extra special groups, because they are the natural generalization of groups of size p cube. So what are extra special groups? For me, it was a new thing because I'm not a group theorist. So these are basically p groups whose center is cyclic of order p, and G quotient of the center is elementary abelian. And actually, more precisely, it's the central product of p cube size groups. So the right way to think of it is, you have, say, L many groups of non-abelian groups of size p cube. What you do is you think of it as a direct product of these groups, and then because they all have centers of size p, those centers are all isomorphic to each other. So you can paste them together by forming a diagonal subgroup of the product of the centers, and that becomes the center of the extra special group. So that's what it is. So what is the size of an extra special group? It's you have L many p cube groups. So the centers are all glued together. So that contributes only a factor of p, and you get a p squared factor from all the GIs. So it is p to the power 2l plus 1. And that's what it is. And it turns out that very similar to the case of p cubes, the maximal cliques are easy to spot. They all have a nice structure. They're all of the same size, of size p to the l plus 1. And there are exactly p plus 1 to the l many of them. But there are many of them, and they intersect in somewhat complicated ways. And I think I'm missing the last, no, it's fine. So we're still not yet fully done with recognizing the commuting graph of an extra special group, because you're just given the graph. You can find all these maximal cliques, and you can see their intersections, but we still have to figure out how to put the group element labelings on all the elements so that it really becomes the commuting graph of the extra special group. So yeah. So here's one quick point that I wanted to make here with this group of size p cube. Notice that there are actually two different non-isomorphic groups of size p cube. One of them has all elements of order p, and the other has some elements of order p square. but the commuting graph structure is the same. It is the sunflower structure in both cases. And even in the case of extra special groups, there are essentially just two non-isomorphic extra special groups. And they both have the same commuting graph, but we're still not done with the recognition algorithm yet. So moving on. So then so the next thing that actually Peter pointed out to me is the right notion of comparing groups in order to compare their commuting graphs is this notion of isoclinism. Let me quickly tell you what it is. So we are working with this coarser equivalence relation. G1 and G2 are equivalent if they have the same commuting graphs. Question is, can we capture this group theoretically? Is there a group theoretic characterization that captures exactly this? And it looks like isoclinism comes close to it. So what is it? So the commutator map of the group G is essentially a map from G quotient the center cross G quotient the center to the commutator subgroup G prime. What it does is strips off the center elements and it's just the commutator, A, B, A inverse, B inverse. It's just a map. And the two groups G1 and G2 are said to be isoclinical if G1 quotient its center is isomorphic to G2 quotient its center, and moreover their derived subgroups are both, their commutator subgroups are isomorphic, and these isomorphisms commute with the commutator map. In other words, what it means is that if I want to apply the commutator map of G1, so I'm going from G1 quotient Z1 cross G1 quotient Z1 to G1 prime, I can come via these two isomorphisms, come down to G2 quotient Z2 and come down to G2 prime, and it would fit nicely together. So the map commutes. So why is this interesting? It's because if G1 and G2 are isoclinic groups, then in fact they have the same commuting maps. It's easy to see because G1 quotient Z1 and G2 quotient Z2 will have the same commuting maps. And with this additional property given by the isomorphism of the commutator subgroups and these two things, these two isomorphisms fitting nicely with the commutator map, allows you to blow up the vertices of these quotient groups into the entire cosets of the centers, and you can put the edges correctly, and you will get the same commuting graphs. The interesting question is whether the converse is true, and I don't know the answer yet. Probably not. It's too good to be true. As Peter said, that it's unlikely to be true. But if it were true even for nilpotent groups of class 2, it would be very interesting because it would even give an algorithmic approach. Maybe. That part is still open. So I'm in fact well ahead of the time allotted. So I'll just quickly wind up with two algorithmic observations. The first is this very interesting result by Solomon and Walder of 2013. They show that non-abelian simple groups are characterized by their non-commuting graphs, therefore by their commuting graphs as well. So, and you can make it, you can easily make it algorithmic. It doesn't give a very efficient algorithm, but it gives you some algorithm. So here is the idea. We use this classification of finite simple groups. So you can check whether given a group by a multiplication table. So what we can do, okay, here is the idea. We will simply go through, so you're given an n vertex graph. So you know the number n. How many simple groups can have size n? It turns out from the classification theorem that there can be at most 2 different simple groups that can have order n. And so we can pull them out because the orders are known and you can prime factorize n easily. So you can identify these 2 possible candidate groups which can be isomorphic to X and pull them out, and write down their multiplication tables, and therefore get their commuting graphs, and then use a very powerful result of Velassi-Babai of checking the isomorphism of two n vertex graphs in time 2 to the order log n cube. So it's a bit of an overkill to solve this problem, but here is an algorithm. Maybe there are cleverer ways of figuring out if a given n vertex graph is the commuting graph of a simple group. I think that's a very interesting problem to discover a faster, better algorithm. And I've not yet looked into this paper. It's not a very long paper. It's less than 20 pages. In a similar flavor algorithm, which is even more general, is this algorithm for the general case. So the general case algorithm is that the total number of n element groups, there are at most n to the power order log n square many n element non-isomorphic groups. So this is a non-trivial theorem starting with, I think, the work of Peter Neumann and spread over several years before it, probably around the turn of the century or sometime earlier than that. It was called. So there's something that there is a follow-up result which can be used to design an algorithm, and that follow-up theorem is by a bunch of 5 authors who are, I didn't generate the BIP file for this, so it's missing here. It's Babai and a bunch of other people, Cantor and others. What they proved is that any group of size n has a presentation, a generator-related presentation of size order log n cube. Not all finite groups. If you leave out finite simple groups of a certain group of Lie type called the Re group as a section, you leave that out, everything else has short generator-related presentations. So here is a very simple idea. Because these are just a small number of them, we can cycle through all of them. This theorem is also effective. That means if you give me the generator-related presentation of an n-element group, I can actually find the multiplication table for the n-element group quite efficiently. So therefore, we can cycle through all these generator-related presentations. These are like compressed groups, so to speak. You can uncompress them like an uncompressed file and extract the group multiplication table from it and check if it is isomorphic, if its commuting graph is isomorphic to the given graph. That's a horrible algorithm. It's very brute force, but its running time is 2 to the order n cube, log n cube, sorry. So with that, I come to the end of my presentation. Maybe Peter would like to add something to it, some questions, some further thoughts. Let's leave it there.
Okay, well, thank you very much, Arvind. Let me just add a couple of things, if I may. First of all, there are at most 2 finite simple groups of any given order, but I believe it's true that these 2 groups can be distinguished by the conjugacy class sizes. And of course, from the commuting graph, we can easily read off the conjugacy class sizes. So we don't need to do a lot of graph isomorphism to check that. We could, well, we need
eliminate one of them. Eliminate
only one of them. So there's only one that we have to do. So we can simplify things a little bit there. And the other thing you just made one slight slip earlier on when you were talking about isoclinism. If 2 groups are isoclinic, if they have the same order, then their commuting graphs are isomorphic. But they may have different orders.
Yes. Sorry. Because the centers could be of different sizes.
The centers could be of different sizes, exactly so. But that's the only thing I guess that's the only thing I have now. I'm sure I will have other ideas later, but I don't have anything else to say now. But thank you for the talk.
Thank you.
Okay, thank you, Arvind. We will have more discussions towards the end of the program.
Yeah.
So invite Sandra. Sandra is there? Yeah. Sandra Kingan is from City University of New York.
Thank you. I'll share my screen. So I'd like to begin with a big thank you to Vijay for inviting me to join this group, and Aparna for the incredible organization and smooth functioning of this group. Many thanks to Peter for the wonderful introduction to the area and all the other speakers. I really liked Arvind's problem on since I also like algorithmic thinking, and I'm thinking more about his problem than my own talk right now. Yeah. All right. So this
Welcome.
is I have a talk that I couldn't find a title for it, and I couldn't also find an abstract. So yesterday I emailed Aparna and saying I don't have a title or abstract. I have a talk. This is not my specialty, and my area is mainly graph structure theory. Yeah, and so I've been in graph structure theory for a long time, and then I discovered this other area because it was appearing as many symposiums in conferences, structured family of graphs. And for quite some time, I didn't quite see the D over there, and I was always wondering what's the difference between structured families of graphs and graph structure theory. And there is a difference. I'm not sure I can totally articulate it, but I do see a difference now. And I feel like there's some unexplored territory between these two areas. We tend to be really siloed in our specialties. So as notation, I'll use G for group and gamma for graph, as has been used so far. So the starting point for my thinking is when Peter mentioned a gamma is a cograph if it has no subgraph isomorphic to P4, no induced subgraph isomorphic to P4, the 4-path. And it's a cograph if and only if its co-kernel is the one vertex graph. And the co-kernel is obtained by fusing twins. And twins are vertices that have the same neighbors, possibly accepting each other. And that was the example in Peter's slides. And then I wanted to mention split graphs, which sort of came up in passing. Gamma is a split graph if its vertices can be partitioned into a clique and a stable set. And a split graph can also be characterized by its forbidden induced subgraphs, namely C4, the complement of C4, and C5. So in the class of structured families, and cographs and split graphs are considered structured families, lies the class of threshold graphs. Gamma is a threshold graph if it is uniquely determined by its degree sequence, and threshold graphs also has a forbidden subgraph characterization. So I'm interested in the class of graphs that are not threshold graphs. Such graphs can be obtained from each other by what is called the two-switch operation. So what's a two-switch? So if you have two edges, A, B, and C, D, and there's no edge between A and D and B and C, there might be an edge between A and C and B and D, then you can remove these edges and replace them with these edges. And G and H are if G and H are two graphs and n vertices, then they have the same degree sequence, which, by the way, is I mentioned that is a way to related to the threshold graph there. So G and H have the same degree sequence if and only if G can be transformed into H by a sequence of two switches. Now, this is an old result. It dates back to Havel Hakimi in the 1960s and Berge. so if you have threshold graphs, if you think of the class of graphs as the big square box here, then threshold graphs are uniquely determined by degree sequences, but degree sequence does not determine distinguish graphs outside here in the yellow area. But the graphs that are here, if they have the same degree sequence, and you can get from one to the other by the two-switch operation. So in lecture 2, Peter has said, when is the power graph a co-graph? And that's the problem that I'm interested in. I don't have a solution, so I don't want to raise any hopes here. When is this? I mean, I want to know when is the commuting graph, the threshold graph. In the hierarchy, I see that power graph is at one end and commuting graph is at the other end. And also, I want to know when is the commuting graph not a threshold graph. And then I want to think about commuting graphs that have the same degree sequence, that don't have, that have the same degree sequence, because then you can go from the commuting graph of G and the commuting graph of H by a sequence of two switches, right? So you have groups G and H, and the commuting graphs G and H have the same degree sequence, which means you can get from G to H by a sequence of two switches by the previous theorem. So then reflect that back, or take that back to the graph, and I want to see what, to the group, and I want to see what happens to the group. What does the two-switch operation mean for the group? So, can you get from one group G to the other group H by some analog of the two-switch operation in the group? So that's one thing I wanted to look at. And the reason I sort of thought in this direction is on this slide here. So you have a degree sequence, and then one step further generalizing that would be the neighborhood degree list of a vertex. So it's so here you have the vertex V, and you have all its neighbors here, sort of like a concentric ball around the vertex V. And the neighborhood degree list is a list of the degrees of vertices. It was 2018 that Barris and Donovan sort of came up with this notion. Their paper on archive is 2015, eventually published 2018. Not sure what the giant length of time between one concept and the other, why that is the case. And they gave us characterization of what they call NDL unique graphs that have the same neighborhood degree list, and it's very closely related to two-switch with some extra conditions. So now yellow box has gotten a little smaller. So you have threshold graphs here, and which are basically degree sequence unique graphs, those that can be determined by their degree sequence. NDL unique graphs are those that can be determined by their neighborhood degree lists uniquely. And here, NDLV does not distinguish graphs here. And Barris and Donovan also determine how to get from one, if you have two graphs with the same neighborhood degree list, how you can get from one to the other. And this is where we come in, with my colleagues Nadia Benatli and Ezra Hallett. So we just took that to K neighborhood degree list. Again, wondering why this concept took so long to originate. So K neighborhood degree list of a vertex V is just a list of the degrees of the vertices in the K neighborhood. So now we're looking at concentric balls of vertices here. And a picture of graphs that cannot be uniquely determined by their neighborhood degree list, NKDL for K equals 1, 2, 3, 2. The diameter has greatly shrunk, but it's still there. Otherwise, we would have solved the isomorphism problem. So there are still graphs in the gray area. And we gave a characterization for N2DL unique graphs with diameter 2, and we're writing up a paper where we extend that to NPL to a larger family than diameter 2. Still, the small cycles are a real problem when you're trying to generalize from NDL to N2DL. And if we can handle the small cycles, I think we can go all the way to NKDL. So that's one connection, and I felt like those problems on, so this is independent of groups, but I think I can link some of the group problems to this and use this thinking and expertise in this particular area on those problems. And then in another direction, also starting out with a co-graph, and this is I'm really keen on this because it relates to my bread and butter results on excluded minors and forbidden induced subgraphs and things like that. So consider the graph. You take gamma and you look at all the class that has no class of graphs that has no induced subgraph isomorphic to gamma. And again, Peter mentioned this in his result, lecture 2, that gamma be a twin-free graph, and then another graph, delta, is in the forbidden another graph, delta, has no induced subgraph isomorphic to gamma, if and only if the co-kernel of delta is also in this class. So and then Peter made this comment: if U and V are twins in gamma, then the transposition of U and V fixing all other vertices is an automorphism. So if you're interested in automorphism group of a graph, then carry out twin reduction. And as soon as I heard it, I thought, yes, I'm very interested in the automorphism group of a graph. And so this is another avenue that I am definitely pursuing. And recently, there's been some work on twin width. That's a group of people and have just put out a paper on arXiv. Actually, 4 papers. It goes twin width 1, 2, 3, 4, and they've given some talks. And this is sort of where I stopped. This is like the next thing. So I feel like I can relate those two. Not entirely certain how that would relate to groups, but it's certainly something that came out of this research discussion. And I just wanted to sort of do a little bit of a mind map. This is my last slide. So we start with co-graphs, then threshold graphs. That goes to, you can generalize that notion to NKDL unique graphs where K is 1 to the diameter of G. And that's related to the isomorphism problem because the more things you have to distinguish graphs that are easy to calculate, it makes isomorphism easy. And then on co-graphs also relates to twin width, forbidden subgraph characterizations. So the best title I could come up for this talk was Sandra's mind map, and that didn't seem like a good title, so that's why I don't have a title or an abstract. Thank you very much.
Excuse me, what is this twin width?
So
twin width, yeah.
Yeah, it's a twin width. So I read the abstracts of the talks a little bit, and I believe that twin width is the number of twin reductions you need to do to get down to the co-kernels. So the twin width of, for example, they said the twin width of co-graphs is 0. So the terminology is very different in this group's work. So I've been sort of trying to translate it. So as best as I understand it, is the number of twin reductions that you can do to get down to something that may not have a twin, won't have any more twins. But I can't be 100% certain about this because I'm doing a translation from their terminology to this.
Third speaker is Swathi from National Institute of Technology, Calicut. She is a doctoral student. So Swathi is present.
Yes, yes, sir.
Yeah. Please.
Am I audible?
Yes.
Okay. I'm Swathi. I'm a research scholar at NIT Calicut. I'm doing my research under Dr. MS Sunita. Here I'm going to discuss a few results on matching in power graphs of finite groups. Like GBA finite group, the undirected power graph gamma of G is a graph with vertex set to G in which two distinct vertices A and B are adjacent if and only if A power n equal to B or B power m equal to A for some positive integers n and m. Clearly, gamma of G is always connected and is complete if and only if G is a cyclic group of order 1 or P power n for some prime number P and positive integer n. Now, a matching or an independent edge set M in a graph gamma is a set of edges in which no two of them are adjacent. That is, no two edges share a common vertex. A vertex is matched or saturated if it is incident to one of the edges in the matching. Otherwise, the vertex is called unmatched. Okay. A matching M of a graph gamma that is not a subset of any other matching is called a maximal matching. And a matching a matching that contains the largest possible number of edges is called a maximum matching. The size of a maximum matching in a graph gamma is known as its matching number. A perfect matching is a matching which matches all vertices of the graph. So now we'll move to some results on matching in power graphs of finite groups. A GBA finite group of order n, then the matching number of course is at most n by 2, and this upper bound is obtained by the graphs possessing perfect matching, and for that n must be even. Okay. So if G is a finite group with odd order n, then the matching number of gamma of G will be n minus 1 by 2. Here, if we take an element x, then that x is adjacent to its inverse. Therefore, taking the edge set M as x inverse where x belongs to G difference C is a maximum matching in gamma of G, where E is the identity element in G. Okay, so if let G be a finite group with a unique involution, then gamma of G has a perfect matching. Clearly, since x is, if x is an involution in G, then taking the edge set y inverse, where y in G and y not equal to x comma E, together with the edge Ex is a perfect matching in gamma of G. Therefore, this theorem proves that the power graph of every cyclic group of even order possesses a perfect matching. So let G be a finite group with order 2 power n, then gamma of G has a perfect matching if and only if either G is a cyclic or a generalized quaternion group. Here the converse is very immediate because the cyclic group of even order and a generalized quaternion group contains unique involution. Therefore, by above theorem has a perfect matching. So let G be a finite group, then the matching number of gamma of G is 1 if and only if G is elementary abelian group of even order, or G is the cyclic group Z3. And let G be a finite group, then matching number is equal to 2 if and only if G is either cyclic group of order 4 or 5, or the symmetric group S3 of 6 elements, or the dihedral group D4 of 8 elements. Here the dihedral group Dn of order Dn is of order 2n is the symmetric group of symmetries of the regular n-gun. Clearly, for n greater than 1, the power graph of Dn has more than one pendant vertices adjacent to the identity, and hence power graph of Dn has no perfect matching. And the matching number of power graph of Dn is the ceiling function n by 2. So let G is a finite group with order 2 into p power n, where p is an order prime. If G is an EPPO group, then G has no perfect match. An EPPO group is a group in which every element has prime power order. So these are the few results I have obtained on the matching number of power graphs.
Any comments from the audience?
So my...
Can I ask a question, please?
Yes.
The matching number, you know when the matching number is n over 2 or n minus 1 over 2. Can you say anything about n minus 2 over 2, n minus 3 over 2, and things like that?
Sir, actually, I'm working on that. I didn't get much results on this. I presented this here because I want to know that whether is that significant to find the matching number of these power graphs, and is that significant to find a group that whose power graphs having a perfect matching like that.
Well,
I need some suggestions. And
yes, I will think about that, but I think potentially it is interesting, because certainly results about clique number and independence number of these graphs are very interesting indeed, and matching number is a similar kind of parameter, so I suspect there will be interesting results for that also. But if I have any ideas, I'll certainly pass them on to you. I don't think I have anything much at the moment. I haven't thought about the question of matching number, but it's a nice idea, and you've got some nice results already.
okay, thank you, sir.
Perhaps I can please.
Thank you, Swathi.
Do we have a moment?
Okay, thank you, sir.
To say something?
So,
can I just?
Is there anybody else who wants to?
Yes, I was thinking.
Just ask one question on the last. For the last talk, can I just ask one question? Yeah.
Yes.
So can there be the number of match? So suppose we are given a power group and the corresponding power graph. So can there be something like the number of matchings with the matching number n minus 1 by 2 or something like that?
Yeah.
So
it's also possible. Till now, I didn't check that result. I didn't work on that. It may be. I think it's possible to find.
Okay.
May I ask a question? Can you hear me?
Yeah.
Okay. So, maybe I just have a suggestion. There's a very nice algorithm for finding the matching, maximum size matching. It's called Edmonds Blossom algorithm, and it's a polynomial time algorithm for finding the maximum matching in a graph. And so maybe that can help you.
Okay, thank you, ma'am. Can you please again tell that name of that algorithm? Edmonds
EDMONDS, Edmonds, Blossom, BLOSSOM, algorithm for finding the maximum size matching.
Okay. Okay, thank you, ma'am.
You're welcome.
So, anybody else? Does any participants want to say something?
I had a quick question for Swathi. What do clicks in power graphs correspond to? Are they cyclic subgroups or?
Up to my knowledge, it's some already a formula is given. There some that's
Maximal clicks, at least.
maximal clicks. Yeah.
Can I say something about that, please? Yes.
Yes, sir.
So maximal cliques in the enhanced power graph are maximal cyclic subgroups.
I've forgotten the definition of enhanced power graph.
Okay, so you join two elements x and y if there is another element z such that both x and y are powers of z.
Ah.
Right?
Okay.
So that's the enhanced power graph. And so another way of saying that is that you join x and y if the group generated by x and y is cyclic. And if you think about it like that, you see that the maximal cliques are the maximal cyclic subgroups.
Okay.
Now, to go from the enhanced power graph to the power graph, any clique in the power graph is a clique in the enhanced power graph, and therefore it's contained in a maximal subgroup, maximal cyclic subgroup. So you have to just look at the maximal cyclic subgroups and find the maximal cliques within those. And there is a formula for the size of a maximal clique in the power graph of a cyclic group. And so from that, you can work out what it is in an arbitrary group.
Okay.
So this is interesting stuff. And perhaps, Vijay has said that he might let me say something again in the last meeting of the discussion group. And that's one of the things that I would put in.
Fine.
Yeah. There's a very nice result about that. So in fact, let me just tell you now, because I like this so much. So what's the size of the largest clique in a cyclic group, in the power graph of a cyclic group? Well, it's bounded above by a constant times Euler's phi function of the group order. And this constant is about 2.65 something or other. I know it at 10 places of decimals. It's easy to compute. And there's even a formula for it in terms of a sum of products over the primes. But so it's a nice little bit of number theory.
Mm-hmm. So, but group theoretically, what would that object be? Really, it's every element is a power of all elements are powers of each other.
No, so yes, so in a clique in the power graph, if you take any two elements, one is a power of the other, and you can prove from that it must be contained in a cyclic subgroup, but it won't in general be the whole cyclic subgroup. So you have to look at the cyclic subgroups and find the maximal cliques within those.
Okay, it's because the generating elements clearly will be co-prime to the.
Yes, say, let's do an example. Let's take the cyclic group of order 6. Then a maximal clique in the power graph will contain the identity, will contain the generating elements, but then you have a choice. You can either put in the element of order 2 or you can put in the two elements of order 3, but you can't have both because the elements of order 2 and 3 are not joined in the power graph.
Okay. And that's where the third element comes into. So the enhanced power graph gets around
in the enhanced power graph. They are all joined because in the enhanced power graph, everything is a power of the generator of the cyclic group. So the enhanced power graph of any cyclic group is complete, but the power graph it isn't. And there is a way of finding the maximal cliques in that.
Okay, interesting.
Suppose you have a power graph of some group G and another power graph of some group H. You take the Cartesian product of that power graphs. Does it come as a power graph of something in the groups? No, not audible.
Not always. Not always. No, in fact, that's fairly unusual for that to happen. I can't remember now. I thought about this once, but I can't remember at the moment what the answer is. But you can say something.
I see. Okay.
Yes, I mean, if you're taking products, then the commuting graph is easy, but the other graphs are more difficult.
So with that, we come to the end of today's session. The next speaker will be, again, Prof. Arvind from IMSC Chennai. He will be talking on random sampling from finite groups via expander graph. So see you all on 16. Thank you.
Thank you.